Hello, everybody. Thank you for joining us for the workshop this afternoon. It's all about probability, probability diagrams, trees, contingency tables, and Venn diagrams. So first of all, we'll tell you who we are. I'm Tony Bearden. And about 20 years ago, I set up AIMSEC, and about 10 years before that, the Enrich website. So I've been very involved with sharing ideas and our enthusiasm for mathematics with teachers and children worldwide through the internet for, as I say, for a long time. So hand over to Caroline and she will introduce herself.
Hello, my name's Caroline. I'm the founder of Bubbly Maths, and the reason why I do what I do is that every child on earth will enjoy learning and be able to do mathematics. And what better way to achieve that than to work with teachers to share Tony's amazing activities.
So what about you, Temba? Please introduce yourself.
Greetings to everybody. My name is Wetemba Michael Moyo. I'm based in Cape Town as a lecturer at AIMSEC. I originally come from Zimbabwe. Today, I'll be with you on this GTEN workshop together with Tony and Caroline. Thank you.
So the program for today, what are we going to try and do together today? Well, first of all, when you see this green text, this green writing, that's a signal to you to answer a question. So get your thinking caps on because we want you to participate. Now, every time we're planning something on one of these GTEN workshops, we're looking at this spiral learning, okay? So wherever you are on this spiral, whether it's grade 7 or grade 12, the basics, the foundations for those ideas, which you now have to teach to your classes, they will have been, those basic ideas will have been introduced much earlier for those children. So we start developing the important ideas right soon, even before the children start school. We start helping them with number sense, counting, and then build on all of this year after year, grade after grade. So we're going to introduce some activities that are suitable for younger children and throughout the grades and suitable for the school leaving year as well. So we're working on calculating probabilities. We'll introduce the pigeonhole principle. We'll look at how tree diagrams help us to work with probability and contingency tables. Now, contingency tables are otherwise called two-way tables or sample space diagrams. We'll come back to them. And finally, Venn diagrams. So there are 3 ways of illustrating the probability of actually putting all the information in a very clear way into a diagram. So starting off with the idea, we're going to start off with this simple idea, at least one. It's all about children in families and equally likely events. So even quite young children understand that if you toss a coin, there's equally likely to be heads or tails. And we draw a sort of associate or draw a parallel between tossing a coin and is the new baby going to be a girl or a boy? Okay. And then we look at the difference between probability experiments and theoretical probabilities and how that's important in real life. For example, with medical trials, you know, like we had during COVID, we don't actually know whether this new treatment or new vaccine or what it is, whether it will be effective. The only way we find out what chance it has of, what probability it has of being effective, of working, is by finding out how it affects a sample, a large number of people, so they are taken to be typical of the whole population. So we're going to look at a problem on an epidemic, and here there's no theoretical probability possible. We're going to use tree diagrams, tables, and Venn diagrams. And then we're going to introduce similar problems for different age groups. And we're going to look at contexts, situations where events are equally likely, that means independent, and where they are not equally likely, that means with the second thing, it depends on what happened just before. And that's not true with tossing a coin. If we toss a coin once, and then we toss it again, it doesn't matter whether we got a head or tail. The first time, we're equally likely to get a head or tail the second time. So they are independent events, but other events we'll see are dependent, and we have to take that into account. Pigeonhole problem, yes, we'll come back to that. Use of tree diagrams for dependent events, and then the tree diagram helps us to think about a situation, a problem, but sometimes we don't need to draw the whole diagram, and we're going to focus on a little bit of the diagram and not the whole thing. And then we're going to see how we can calculate results, and even with Excel spreadsheet, and even draw graphs with Excel. And finally, we're going to review what we have done. So moving on. Over to you, Caroline.
Right. So this is your opportunity to have a go. And we're looking at what are the probabilities of heads and tails when you toss a coin. It's a simple question. So what are the probabilities? Toss a coin. What is the probability of throwing a head or a tail? Go ahead and make a comment. And then the next question is, what is the connection between newborn boys and newborn girls and heads and tails? So what is the connection between the two? And what is the probability of 3 tails when you toss a coin 3 times? And why? Why is that probability what it is? What is the probability that if you toss a coin 3 times, there is at least 1 head? And why? So it's probability of 3 tails and at least 1 head. And now moving on to the diagram, you can see that there's 7 ticks and 1 cross. Now, how is that connected? How does that even help you with questions 3 and 4? And there is the side question. If Bussy has 3 children, what is the probability that at least 1 will be a girl? And then there's an extension. We'll move on to that. You can do that in your own time. Now,
we're going to be answering these questions in the next few minutes, but we want you to think about the questions. Okay, so we did have a chat, didn't we, Caroline, before this session with Kutemba about what happens. Is it really 50-50? And we know that in the population as a whole, people, a lot of people don't identify themselves as either male or female, but we're taking a 50-50 chance on each one with newborn babies for 2 reasons. The first reason is that in probability, you actually work with approximations. You know it's only an approximation. You don't have to have exact data, because you very rarely do have exact data. Okay, you assume that your sample, if it's big enough, is representative of the whole population. Okay, and So because it's extremely rare that a newborn baby cannot be identified as male or female, we are making the assumption that this is going to be 50-50. We don't want to offend anybody, but it's not until they're a little bit older that children actually identify themselves as different, and we do respect that. So we're looking here at a problem of children in a family, and we know that young children actually can identify with children in a family. So this is a good problem to do. And we're going to come on to consider the answers to these 5 questions as we move on. So look at these 3 diagrams here. You've seen the tree diagram, and what we've said is the tree diagram for heads and tails is just like the tree diagram for boys and girls in a family. And there's an issue here with language. This title, at least one, we must make sure when we're discussing it that everybody understands what that means. In fact, when it comes to 3 children in a family, it means one of them's a girl and there are 2 boys, or 2 of them are girls and there's 1 boy, or there are 3 girls. So there's at least 1 girl.
Which is every single situation except when there's 3 boys.
Exactly. So then we've left you something to do, because, well, this is a joint effort. It isn't just us telling you. So we want you to fill in the labels that describe the families for the 5 regions in this Venn diagram that are not labeled.
Just go ahead and sketch it out and fill in the missing conditions.
So what you'll see is the red area or region inside the red circle is where the second child is a girl. Okay. And the gold color is where the first child is a girl. So where those 2 intersect, but where the third child is not a girl, so outside the blue ring, you've got girl, girl, boy. Okay, so we have labeled 3 of those regions for you, and there are 5 that are not labeled. So can you label those? Okay, and therefore, and also this sample space diagram is one where we list all the different things that can happen. So we started off making this list for you, and that's girl, girl, girl. All 3 children are girls. And then the first and the second children are girls, and the youngest is a boy. So can you fill in the remaining outcomes in this table?
Again, pause the recording and go ahead and sketch it out. If you were in the group, if you're in the GTEN teacher group, then you can find the worksheet as well.
So now, here you see the answers for our Venn diagram. And what a lot of people seem to do, one of the misconceptions I find with children here, is they consider everything in the rings there, but forget the boy, 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 the one on the outside. So here you see there are 8 regions, and I've filled in them all for you now.
And it's interesting that the boy, boy, boy is the same line on the tree diagram as where the X ends up. So we haven't answered that question yet.
Exactly. But the point is that each of these probabilities, each the makeup of the family has the same probability, and it's a half times a half times a half, because the probability of a boy is a half, the probability of a girl is a half each time. Probability, if they're tossing coins, the probability of a head is a half, the probability of a tail is a half. So it's 1/8 each time, and there's only one of those families that doesn't have any girls at all. So the probability of at least one girl is 7/8, and the probability of no girls is 1/8, and those two probabilities add up to 1. That adding up to 1 is something which we need to have in mind and use, and we use often. So now we'll move on to another, same thing, we're not moving on far. We're going to look at 4 children in a minute, but let's note down, and in a different table, is a sample space diagram, but it's set out slightly differently to the last one because we want to list for 2 children, 3 children, and 4 children here, and we could extend that, okay? So we've just had all that list for 3 children, and so here it is again in this table. And then what we want to ask you to do is to fill in for the 4 children. If there's another child, if there are 4 children in this family, what are the different possibilities? And so the space there in that table to fill those in. So for 3 children, there are 8 possibilities. And the probability of at least one girl is 7/8. What about 4 children? There you go. There are all the family makeup where you can have 4 children, and in only one of them will there be no girls at all. That's the first.
We were talking about how many different people writing out these cases in different ways, because I did not want to write all of the 3 children possibilities another time. So what I wrote is boy and kind of squiggly brackets, and wrote all the possibilities for 3 children, which equals 8, and then girl, and in squiggly brackets, all the possibilities for 3 children, which equals 8, and therefore I knew I had 16 conditions without writing every single one, which you can consider allowing your learners to do that, as long as you can interpret and they can interpret what they have written clearly.
Well, I think Caroline's got it. You see, I made this slide, and my system for making sure I had them all was slightly different from Caroline's, but Caroline has just explained beautifully her system, which was in a way quicker and more efficient than mine. Okay, so the important thing is that there's a system, so you know when you write down all the solutions that you haven't forgotten any and you haven't repeated any. Okay, and systematic working is really, really important in mathematics. So here are our answers, okay, for the 4-child family. And you see the tree diagram drawn again there, and you see now the probabilities on each end of each branch is a half times a half times a half times a half, which is a 16th, and only in one of those cases are there 4 boys. So the probability of 4 boys is 1/16, and the probability of at least one girl is 1 minus 1/16, which is 15/16.
I like to put it in plain English or plain language, and I think of it as, okay, there is only one condition in which they are all boys in this particular example. So it's only one. So possibility, all the probabilities put together up to the fourth child is 16/16, and only one of those is all boys. So it's, you only have to take 1/16 away, which you've done mathematically there. I just personally like to make it into a little bit of a story so that I can make sure that I've got it right. And so I'm like, okay, it's only 1 out of the 16ths, and it's 1 out of the 16th less than 16/16, so that's 15/16. And that's the way I do it.
And that's really helpful, I think. And the principle that carries over throughout our work on probability, anybody's work on probability, is that either an event happens or it doesn't happen. So there's no doubt, nothing in between. So here, that either there are 3 boys or there are not 3 boys. Okay. Sorry.
Yeah.
And or 4 boys and not 4 boys.
Or 4 boys and yeah.
So the probability of event happening added to the probability of it not happening has to be 1. So if you're looking for one of them, you subtract the other. Okay, so let's move on now. So now here's something that we're recommending that teachers use frequently, the idea of a quick quiz where the students put up 1 finger for answer A, 2 fingers for answer B, 3 fingers for answer C, and 4 fingers for answer D, okay? And here's your problem. A bag contains 4 green balls, and 2 balls are chosen at random from the bag without replacement. Now take note of that, without replacement, because we're moving into some new ideas now. What's the probability of choosing at least 1 purple ball? Now we're using the same language, the at least 1 here. So is it answer A or B or C or D? Now the brilliant thing about these diagnostic quizzes is that you can you can absolutely insist on every single learner in the class answering. So have a system.
And they do, even the shy ones, even if they hold it close to them, so you've got to look carefully. It is so powerful, it's surprising. Even the really shy ones will actually respond when they see that everybody is responding.
Yes, so they're not going to be exposed by being asked, because everybody is going to do it at the same time. Now here, look at the question. There's information there, a bag containing 4 green balls and 2 purple balls. So 2 balls are chosen at random from the bag without replacement. Now what that means is that there are only 5 balls in the bag after you've taken 1 out. So the probability changes. So the probability is of the second ball, whatever color, depends on the color of the first ball. So these are not equal probabilities. It's not like the tossing a coin or the children in a family. These are dependent. Okay. Now the labeling on the tree diagram is a bit blurred, and that's a good thing, really, because we want you to read the information and then decide what those fractions should be on the branches of the tree diagram. So you're told that there are 4 green balls and there are 2 purples, so 6 altogether. So the chance of the first one being green is 4/6. And so the chance of the first one being purple is 2/6. And then I'm not going to carry on, but you can work out for yourself what the other probabilities are.
And be careful of the trap of doing it the opposite way around.
And then it's the same language as before. What's the probability of choosing at least 1 purple ball? That means that they're
So
not both green.
you've got all the answers on the left there. But when you present this to the learners, you will only present the question inside the box. You will not present the answers. The answers are there to help you. And when you do this, the system to do it is get them to put up 1, 2, 3, 4 or 4 fingers immediately, all at the same time. So count 3, 2, 1, go. And then don't say who's got it right or who's got it wrong. Get each choose a person from each group to say why they think that's the answer, and they might sort their own. So they might decide, yes, that's definitely the answer. It might be one of those, I think it's that answer, but I'm not sure, and they've actually got it right. But they can then show themselves that they understand it by explaining it to others. Say, actually, no, I'm certain now. I know I've got it right. And then those that haven't got it right, just by explaining it and by listening to the others, they can sort out any confusion they might have had. Very, very powerful. Then you can take another poll again before you actually discuss it yourself as a plenary.
Okay, so it's really powerful, and even the shy ones will be prepared to answer if everybody is going to answer. The spotlight won't be on them. They'll do the 1, 2, 3, 4 fingers. Now, as Caroline's just explained, you're going to ask learners who gave answer A and then B, C, D to explain why they got that answer. Everybody's got to listen and decide, did they choose the right one? And then they're given a second chance. And that's the powerful thing, because they can change their mind. And then as the teacher, you can decide after that whether you need to do some more work on that, because a larger number of the children have not understood. And you'll also be able to identify which learners failed to understand it and which got it right, so that you can give them some extra help. Because if you're going to go on doing further problems like this, you want to make sure that if you're at that stage, that they can do this one. So, and this is a situation where there are several misconceptions that often arise. You know, for example, if you look at B, that's the complement, that's 12/30, and that's the probability of choosing no purple balls, okay? Whereas the answer should be of choosing at least one purple ball, which is 18/30. And C, the learners who gave that answer may well be thinking, probably the second ball chosen is purple. That happens to be 10/30. Learners giving this answer may not have understood the question, because that's not exactly what's being asked. And the learners who have answered D, they may think that the right answer is 2, 6, which is the first purple ball, times 4/5, which is the second ball being green, which is clearly not what's being asked for. Again, they haven't really understood the tree diagram or the question properly. So according to how many are answering B, C, or D, you know what work you've got to do as a teacher to help clear up those misconceptions. So let's move on, but before we do, look at the link at the bottom of the page, because there are thousands of suggested quizzes there that you can use, quizzes like this for all the maths topics, and also all the Aiming High teachers' notes have got quizzes in them as well.
So we've got 20% of the inhabitants have been inoculated against the disease, and the chance of escaping infection, if you've been inoculated, is 90%. If you haven't been inoculated, your chance of escaping infection is only 25%. Now, this is 2 consecutive events, and it is dependent, the second event depends on the first. How are we going to represent this? We have a tree diagram there, which is not complete. So we'd like you to sketch that out and fill in the blanks. Just pause the video while you do that.
And you see that the chance of being infected definitely depends on whether you've been inoculated or not.
Dramatically depends on whether you've been inoculated.
Okay, so our second diagram here is a sample space diagram. This has got other names and it's quite confusing, but we have to use them all because you'll see them in questions and in people talking about the probabilities. But the point about a table like this is it shows all the possibilities. And in this case, you will see that these correspond with the tree diagram. Inoculated and infected, or inoculated and not infected. There are two boxes there. And if they're not inoculated, then they can either be infected, third box, or not infected, fourth box. And then you'll see round the edge of that is places to put the totals, and it should all add up to 100%. And we're using percentages here, but you can equally well use fractions or decimals. And then there's another diagram here. We've just seen the Venn diagram. Here's another one. And here you will see the Venn diagram actually shows the proportions of the population inoculated or infected people. Okay, so...
And always remember outside of the, to put the not inoculated and not infected outside within the rectangle.
And that's your 20% of the inhabitants of the city who are not inoculated and not infected. That's the fifth. Okay. But the ones within the rings also add up to 4/5 if you work that out. We'll come back to that. So this is you'll see it's highly relevant to what's been happening in the last few years and still happening. So we want you to compare the three diagrams and see how they all give you the same information. Now here they are. Now we've filled in the probabilities in the tree diagram. So that's filling in just from the words that were given in the first place, the information there. And inoculated and infected is 1/5 times 1/10, which is a 50th. Inoculated and not infected is 1/5 times 9/10, which is 9/50ths. And you see them in the Venn diagram below. Okay.
And then just go ahead and write out the other two, not inoculated, infected, not inoculated, not infected. Just go ahead and write down the probabilities for those. Pause. You can pause the video while you do that.
Now, the next question is, do these probabilities in the Venn diagram add up to 100%? And you should be able to see that the probabilities in the Venn diagram agree with the ends of the four branches that you're working out.
And both of these are great practical examples of adding fractions or multiplying fractions, between checking that they add up to 1 and processing them. Why do I need to learn fractions? Well, helps you work out probabilities.
Now, we've now put these calculations into the two-way table or sample space diagram. But we still covered up some of the answers to leave you something to think about. So again, you can pause the video and fill all these answers in before you go on playing it you should really try and do it yourself. So here are the answers to the questions we just asked. And you'll see that the three diagrams all agree with each other. And if you look at what's happening now, you'll see the how the probabilities are worked out in the tree diagram. So the people who are inoculated and infected is 1/5 of times 1/10, which is 1 in 50. That's a very low proportion of the population. Whereas if they're inoculated and not infected, that will be 9/50, and or 18%. And you can see then infected, if they're not inoculated, what proportion of the population will be infected? That's 4/5 times 3/4, which is 3/5. So that's quite a high proportion. If they're not inoculated, 60% of them will get infected. And finally, you'll see that your 9/50 and 1/50 add up to 10/50, which is 1/5, and 3/5 make 4/5, and the 1/5 outside both of those regions adds up. Everything adds up to 100% or 1.
And this win probability is really important discipline to always check that, to always make sure you add up to 1 or 100%. In the same way, if you're doing the inverse operation, if you've done, if you're adding, check your answer by subtracting. With probability, being in the habit of making sure you've got a 100% or a probability of 1 is a really useful discipline that's going to catch problems that learners can make sure that they're checking their own results.
So why teach probability, Caroline?
Well, it says here we need to give children the best possible opportunity to thrive when they leave school. And knowing probabilities is, apart from the fact that this is something that is really used if you're in sales, if you're in science, if you're a scientist in any way, if you are working in working with statistics in journalism, or even local government, statistics and probability. These are things that are used in everyday life, and also interpreting. So interpreting what you're seeing, interpreting data, interpreting it, just making intelligent an analysis of numbers that you see in the real world. And in the job market, where we can use calculators, we've got computers to do the things involving facts and skills that are perfunctory. Humans have to be able to solve real life problems. Humans in a job have to provide skills that only humans can provide. And despite all this AI doom and gloom they've been coming up with, and rays of hope and doom and gloom, it's humans that are controlling everything. And when you're collecting and analyzing data, probability and statistics can be applied in so many ways to predict outcomes, to do risk analyses. I didn't mention insurance. People that work out whether or not there's a lot of jobs in insurance to work out the risk assessments, and what and how much each individual should be charged for different types of insurance. And you've got clinical trials, we're going back to the medical fields, and weather forecasting. It's all about probability with weather forecasting, and so much more. And it's being able to analyze those numbers and having the ability to do that using the human brain as opposed to a computer, that's where your learners are going to be able to shine above the computers. They've got the ability to think and understand
In the
probability.
first place, they're more likely to get a job, a job that was well paid, if they have this sort of understanding. And it is important, as Caroline has been saying, because if they become adults and don't understand probability, there is a whole huge range of aspects of life that they're completely childish in, because they still don't understand how the world works. So if they're going to understand how the world works, they need to understand probability, the principles, the fundamentals of probability.
I use the word hoodwinked. If the hoodwinked means you can be conned. You can be conned into believing something that isn't the case. Like, for example, 10% of people use our product. Well, actually, if you read the small print, it's 10% of the people that they polled use the product. You don't know if that was 10 people or 100 million people. It really, really matters as to the detail and statistics and percentages and things can be really distorted to put across politicians, newspapers, sales, marketing. They can hoodwink you into believing something different. So you've got to be able to understand it and look at the whole situation to actually know what they're saying to you.
Right. We are going to look at 3 similar problems. We need to know whether successive events are independent or not independent. Remember, we said independent events are those events which do not interfere with one another, while the dependent one will always, an event will always be, dependent on what happened in the previous event. So we look at 3 scenarios here. We have the same problem suites. 6 bags each contains suites of 5 different colors in equal numbers. You pick 2 suites at random from different bags. What is the probability that they will be the same color? We have colors green, white, yellow, orange, and red for these suites. Just think in a moment on what could be the probability that they will be the same color. The other scenario is the same birth month. What is the probability that a group of people, from a group of people chosen at random, 2 people will be having the same birthday month? The other one is 2 people having the same birthday, date of birth, that is the same birthday.
We're looking at the difference between an independent situation and a dependent situation. So the question is, why? That's what we want to answer in the chat. One word, why? Why does the first depend on the birthday of the first person?
Let's look at each scenario first and then critically think what could be the reason that you find 2 suites of the same color, 2 people chosen from a group of people who were born in the same month, 2 people chosen from a group of people who were born on the same day.
When do later people or events depend on earlier events? And when are they independent? And why? Think of that question. In your heads, think about the difference between independent events and dependent events. Okay, and we'll come back to it. We'll make sure that it does get answered.
Now look at the same color sweets, the green sweets, white, yellow, orange, and red. You have those 5 different packets. There are 6 bags, each contain green, white, yellow, orange, and red sweets with equal number of sweets in each, for each color. We have 5 different colors here. When you pick sweets from different bags without looking, that is randomly without looking, what is the probability of drawing a yellow sweet? Is the probability the same for the other colors? If you pick 6 sweets, 1 from each bag, what is the probability that you'll get 2 of the same color? Just reflect on those questions. How would you answer a problem like this?
What's the probability of drawing a yellow sweet? There are 5 different colors. Is the probability the same for the other colors? Yes or no? And if you pick 6 sweets, 1 from each bag, what's the probability that you'll get 2 of the same color? And there's a hint, big hint, and a picture, and in red writing there.
Another hint is just think of the probability space generated by this event, that is 5 green colors of sweet. If you can create that, you'll find it much easier to solve the problem.
Nelly, see where it says all the sweets have the same probability in each bag?
But let's look at this pigeonhole principle. Supposing the pigeons have to go into the boxes, and there are more pigeons than boxes, then some boxes will have more than 1 pigeon. I think that is obvious and common sense, and that is a principle. So if you pick 6 sweets, 1 from each bag, and there are only 5 colors, then you must get 2 of the same color. Because if the first 5 you pick are all different colors, you've got all possible colors. So the 6th one, just like the 2 pigeons having to go into 1 hole, the 6th one must be one of the colors you've had before. So when you reach 6 here, because there are 5 colors, the probability of getting 2 of the same color is 1. It's bound to happen.
So we're picking 2 sweets at random from each of the different bags. So we're asking a very specific question. If you pick 2 sweets, what is the probability that they will be the same color?
So let's be clear, you pick the sweets from different bags.
And Tony's just given you a hint to help you find it out. If you complete the 2-way table,
you realize that in this case, a 2-way table works out much easier as compared to using a tree diagram. That's why you have to have expose learners to different ways of solving such problems. They will obviously gain skills in saying, okay, in this case, when I have 2 sweets of the same color, white, white, orange, orange, red, red, and so forth, out of how many possibilities? So that obviously makes you think of what is it? The space diagram which Tony has just put on the board. If you can just complete it, then we can easily give solutions to the problem.
That answer comes out quite quickly. If you start drawing a tree diagram here, you quickly think, oh, life is too short. So, and then if you draw a space diagram, oh, wait a minute, we just have to be systematic here. So you can use logic and you allow the learners to make the mistake or do it the hard way, and then we go, actually, what if you did it this way? And I have completed the space diagram. Cynthia, 20%. So Cynthia has represented it as a percentage, and Llewellyn as a fraction. And guess what? They're both correct, which is lovely.
So the highlighting there is where the
Very
sweet
good, very good.
colors, and there are 25 possibilities. And in 5 of those, the 2 sweets are the same color.
And Nellie Seaway has said it's 5/25.
Yes.
Very
Yeah,
interesting.
a different way of saying it. And that's what I did, Nellie Seaway. I liked that idea. I could see there were 5, I could see there were 25, 5/25, and then I simplified it. That's how I did it. That's the way my brain works. Nice and systematic.
And so we've got 2 probabilities there that the second sweet is a different color from the first. And you'll see why we're suggesting we think about that, because that's going to be how we're going to think about some of the problems that follow. And a tree diagram in this question, for this same sweets problem. And here we are, a tree diagram. Okay. So what we've got here is the same problem, exactly the same problem. Temba just said the tree diagram was a bit tricky to draw, and I think we got all the answers without it. But here it is.
I have to say, Tony, I love this. It's like you do not have to draw the whole tree diagram. And I'll just give you a little spoiler alert. That's the point of this whole session.
So we have 6 bags here, and from the first bag, you draw, it doesn't matter which color. The question is, what happens? Is the second color the same as the first, or is it different? Well, there are 4 more colors, and so in 4/5 of the cases, the second color is different from the first, and in 1/5 of the cases, the second color is the same as the first. And then when we look at the third color, we now have only if the second color was different from the first, then 2 colors have been chosen. So there are only 3 different colors, and the probability that the third color is different from the first 2 is 3/5, and you multiply those together. When we come up to the 4th color, 3 have already been chosen. If they're all different, and they're going up the top of this tree, and at this stage there are only 2 colors left, so we multiply by 2/5. We go on to the 5th color, and now 4 colors have been chosen, there's only 1 left, so the probability that they're all different is 4/5 times 3/5 times 2/5 times 1/5. And then we've chosen all 5 colors, so the probability that the 6th color is different from the other 5 is 4/5 times 3/5 times 2/5 times 1/5 times 0/5, because there's no different colors at all. So that probability works out to be 0, and that is the pigeonhole principle. So the probability for the 6th color being the same as the one chosen is 1 minus 0, so that is 1. 6th color must be the same as one that's happened before.
Llewellyn has also given an explanation.
So he says the first sweet can be any color.
Yeah.
Since there are equal numbers of each color in the second bag, the answer would be 1/5. One doesn't even need to draw up a table or tree diagram. Yes, but then when we're going on to 3, 4, 5, and 6, and the reason we're doing this is not because we need it for the same sweets problem, but because if we've understood it in a simple case with this same sweets problem, then the next 2 problems will be easier to understand. So this question, what about picking 3, 4, 5, or 6 sweets from different bags? In these cases, what's the probability that 2 sweets chosen will be the same color? you just take 1 minus the probability that they're all different colors. And it's, you know, an echoing back to that Elise problem about the children in the families. And we're going to think about this method when we come on to the next one as well.
Tony, probably can I just share one way of maybe understanding the concept of this pigeon wall? Let's suppose you have 7 learners, all of them born different days of the week, and we know there are 7 days in a week, isn't it? One learner is born Monday, Tuesday, Thursday, Tuesday up to the end of the week. There are 7 inside. Then you just pick another learner outside the classroom randomly and bring that learner into the classroom. We now have 8 learners. You realize that out of that group, it's a definite thing that 2 learners will emerge that they were born on the same day. Because we have 7 already born on Monday, Tuesday, Wednesday, on each day. There's equal chances of being born on a particular day of the week. So any child who is brought in will obviously have a birthday on Monday or Tuesday or Wednesday and so forth. So with that concept, you can realize, it is exactly what Tony was explaining in terms of the pigeonhole principle, you know.
What you should see here is that in each case, the 2 probabilities across a row are the same, add up to 1. So for example, 0.8 and 0.2 add up to 1. The probability that 2 sweets picked are all different colors, and the probability that 2 picked at least 2 of the same color, those 2 probabilities add up to 1, the same all the way down the column. So what about this problem? Temba was talking about weeks. Now we're going to talk about months of the year, and in a group, and here's a graph that shows the results actually for groups of 1 up to 12. What's the probability that 2 have birthdays in the same month?
In a group of 13 people, it is certain that 2 people in the group were born in the same month. Why? Well, making analog to the question of people who were born on the same day, let's try and think here. We have 13 people, and out of this group of 13 people, what is the probability that 2 from the group were born on the same month? Remember, we have 12 months in a year.
So go ahead and answer on the chat. What is the probability and why?
I've given you the answer because I think I'd like you to think about it and look at the graph, look at the little bit of the tree diagram. We don't actually need to give the whole tree diagram. We need to follow the same method each time. And this method is just like the method we used for same sweets. We talked about this, Kutemba. Your birthday was in January, wasn't it?
Yes.
Caroline's in February and mine's in March. So if we say the first person was Temba, now the probability that Caroline's birthday is different from Temba's is 11 out of 12. If she was born in the same month, that was January, we know her birthday, but that's and is different. So the probability that the second person has a different birthday from the first is 11/12, and then the third person, the probability that their birthday is different from the other 2, there are 10 months left, is and the probability that they're all 3 born in different months is 11/12 times 10/12. And it's repeating that calculation that gives you the answers that are plotted in that graph. So there you go. That's the answer to my 11/12 times 10/12, which works out at about 76%. And so the probability that 2 of the people in a group of 3 were born in the same month is almost a quarter, which is surprisingly high, I think.
Yes, I agree.
And in the same way, we've just repeated the same calculation and repeated it on a spreadsheet, actually, because all we're doing is multiplying by another fraction where the numerator is 1 less than it was in the last time, keeping the denominators the same. The denominators are always 12. But for the next, when we work out the next one, if this is for 3 people that you've got written down there, and the little bit of the tree diagram shows you for 3 people, and the 0.24 there is this in the table there, which was produced by the spreadsheet and plotted on here, for 3 people, 0.24. Okay, so how do we get the next one? Well, we get the next one by multiplying 11/12 by 10/12 by 9/12. Okay, and taking 1 minus that. And so it's a repeat of the same calculation. And when we do that, we work it all out, we get 0.43. And that's for 3 people. No, it's for 4 people. I'm sorry, 4 people. And there's the 0.43 there. Okay. And so just by repeating the same calculation over and over again, we see that as we go, more people in the group, when we come to 12 people, the probability is almost 1. It is actually, to all intents and purposes, 1. But it could be that everybody in that group of 12 has a different birth month. And then with the 13th person, it's certain that there will be 2 born in the same month. So and it
would be very interesting for those teaching senior grades like grade 12. Remember the topic on calculus. You know, if you check as the number of people increases above 12 and so on, it is almost certain that we will find that probability leading at 1. Can you see that 1 there is our limiting value? And as we know from probability theory, probability will always range between 0 and 1. It will always be in that region between 0 and 1. And this graph explains it nicely, how the probabilities vary from 0 until we get to the limiting value, which is 1 in this case. You're not just drawing that analog with what you teach your students in calculus, especially when it comes to topics like limits. It will be quite interesting for them to make those kind of connections.
Absolutely. Now, we want everybody to answer this question that you see on the screen, on the slide there. Now we're going on not to the birth month, but birthday.
Yeah, the actual, not the birthday of the week. This is the actual birthday that 2 people are born on the same day, different years, but same day. And the question is, in a group of 23 people, is the probability of 2 people having the same birthday more or less than 50%?
Now, there's 366 possible birthdays, counting the leap year. Somebody might have been born on the 29th of February. And we're looking at only 23 people.
Everybody have a guess. This is powerful. This is something you can do in your class. It's powerful. Trust us.
We don't expect you to know what the right answer is. We just want you to just think about it and just, you know, gut feeling. Is your gut feeling that it's less, or is your gut feeling that it's more? You can't be wrong here. We're not asking you for the right answer. We're asking you what you think the answer is. The interesting thing is that nobody's quite sure, and you were getting some yeses and some mores. More lesses than mores.
It's leveling out now. We're heading towards 50-50, less versus more.
It looks like people are sort of, guessing rather than saying what they think it might be.
I certainly, the first time I have been asked this question before, and the first time I answered, I just guessed, and I was wrong.
So look at this tree diagram. For any number of people, a small part of the tree diagram is sufficient to show how to calculate the probability that two people in the group have the same birthday. Now, you should see similarities with the other tree diagrams. It's not the same birth month now. It's the same actual birthday that we're looking at. And what you see in the diagram there is for 4 people, A, B, C, and D.
It comes on later, I think.
Questions: what is the probability that 2 people have the same birthday? Now, it's easier to work out what's the probability they all have different birthdays, and then subtract that probability from 1.
So if at least the 1 minus again, Tony.
So for 4 people, the probability that A and B have different birthdays is probability that B is different from A is 365 out of 366. Now notice at each node there are 2 possible events and 2 branches. Either it's the same birthdays or different birthdays. And there's another question there. Why? So the tree diagram will continue, but we're imagining it. This is the beauty of mathematics, that you can have a picture in your mind, but you don't have to have the whole thing on paper, because our minds can contain a lot more, really. Just as, a small child can conceive that counting goes on forever and ever. They don't have to count forever and ever, but they know it can happen. And so in their mind, they're quite convinced that they know about infinity. They know it goes on and on forever. That's infinity. Here, this is going to stop at the 366th day. Why? Why doesn't it go any further? Okay, so the probability that C has a different birthday from A and B is 365 over 366 times 364 over 366. Notice the denominator of that fraction is the number of birthdays in a year. And the numbers on the top tell you that the last person has a different birthday from everybody who's been asked before. And then when we come on to the 4th person, we multiply by the probability that 4th person has a different birthday from A, B, and C. 3 birthdays have been used out of the 366. So the probability that D's birthday is different is 363 over 366. And when you multiply those together, you get 0.98. So the probability that 2 people have the same birthday in a group of 4 is 0.02. So it's not very likely, but it can happen. Okay. So I want you to write down the calculation for 5 people. And now imagine this tree diagram going on. Okay. What would happen for the person, let's say the people are called A, B, C, D, E? What happens for 5 people? And when the calculation for 23 people? Now, we also did this one on a spreadsheet because it would have been not difficult, but tedious to do the calculation. Just multiplying one fraction by another, by another, by another. So Llewellyn gave this answer to why you don't go beyond the 366th birthday as the pigeonhole principle. Okay. We've had that in different circumstances. There are no more different birthdays, just as Temba talked about 7 days of the week, there isn't an 8th day. So here's the calculation you would do for 23 people. So what we've asked you the question about, is it going to be less than or more than? Okay, so the probability that they all have different birthdays is 366 to the power 22 on the bottom. Notice that when we had 4 people, it was 366 to the power 3 on the bottom. One less than 4. Okay. And the difference between 365 and 363 was 2. So the this is the calculation for 23 people. And that works out to be 0.49, calculated to 2 decimal places. And so the probability that 2 people have the same birthday is 1 minus that, which is just over 50%.
And again, we're looking at being super careful about looking, is it that they have the same birthday or different birthdays? And that is, you really have to look at the wording of that word question.
And so what we've got is, for those of you who answered more, yes, it's more than 50%. It's 51%. So if you have 23 people in a group, the probability that 2 have the same birthday is just a bit more than 50%.
Which is a surprise. I found it extremely surprising, and I do love it. And it's a great activity to do in a school. And if you can garner everyone's birthday from the whole school, then these are things you can actually show that.
But most classes in schools are more than 23.
Yeah.
And you can test out, you know, what is it in your class? And of course, you've got more than 23. I've actually gone on in this spreadsheet calculation to show you the answers up to 30.
Nellie Seaware thinks it's great. It is amazing, isn't it? And it's a lovely activity to do with the learners. It's surprising. You can do this as a party trick. If you have a get together with the family, ask that question and then surprise them with the answer. Get them interested in statistics or probabilities.
So do you see how the table works on the spreadsheet? The number of people in the group is the middle column there. So it goes up from 2 people to 30. And the probability they all have different birthdays is what you work out from the tree diagram. And then the probability on the right is 1 minus the problem. So 0.02 is 1 minus 0.8. And when you come down to 23, 0.51, which we were just talking about, is 1 minus 0.49. So you've got the answer for 12 here. Now the answer for 12, right, is shown by that red spot on the graph. And I'm just going to pause now and ask you to write down your readings from these graphs. This graph, these 5 readings. Some of them you'll find in the table, but some of them go past what's in the table. So we want you to read from the graph. If you do this with the learners, then they'll enjoy thinking about it and doing it. Also, they'll get experience of doing some calculations. They might be able to do it on a spreadsheet if you teach them how to use a spreadsheet. And if they haven't done it themselves on the spreadsheet, they can certainly take the readings, which is what you're doing now.
And I have finished.
And taking,
remember, those ratings are points on the graph. So when you give them, we expect you to give us the coordinates of the points. Remember, every point is defined by an X and a Y coordinate. Don't forget that.
And I can guarantee you that my coordinates that I've written down aren't going to be identical to the ones that Tony comes up with, because there's a lot of approximating done with this graph.
okay, there are the
Okay.
coordinates. And as Caroline says, they're approximate. But the 12 and the 23 are ones that are in the table, and the 37 is between halfway between 32 and 42, and it's that point, which is 0.83. The next one is 47, which is 0.96, and 57, which is very close to 1. And so although there are 366 possible birthdays, and this is why it's quite unlikely, sorry, it's not, I'm not saying the right thing. This is why it's quite surprising that it's almost certain that if you have 57 or 60 people, that there will be 2 with the same birthday. And
I just want to say that Nellie Seaway's first and third coordinates are identical to mine. So we both disagree with you, Tony, and agree with each other that it's not precise, because we don't actually have every single intersection. The grid isn't small enough to we're estimating. So the point is, it's all it's approximately right.
So now this is the review, and I hope most of your lessons end with a review of what we've done. And I'd love you to put up your hands and say something about what we've done, what you've learned. And I put on lots of pictures here, lots of tables, graphs, tree diagrams, and Venn diagrams, and just to remind you. So please put it on, put your remark about
the chat
on the chat. What have you learned? Would you use it in class? Which one would you use? What grade? Whatever you want to say. Put up your hand, and we've had lots of answers from Llewellyn, and most of you have given answers on the chat.
You have participated beautifully. Makes such a it's better for us, and it's better for you, and it's better for. Here we go. Llewellyn's written an answer on the chat, Tony.
So Llewellyn says, if a person is born in a leap year, then the probability that their birthday is 29th of February is 1 out of 366. But most people are not born in leap years. So what would, in general, be the probability of someone having a birthday of the 29th of February, or in any other specific date? Well, the answer to Llewellyn's question is that it's not about somebody who was born in the leap year. The point is, if you've got, so we're all adults. So there have been several leap years during the period that we've been alive, and all of us in this room. So yes, I understand what you're saying, and we could have done this same calculation using the denominator 365 all the time, but I chose to actually use 366, which you're going to get nearly the same answers anyway. Probably to 2 decimal places, they'll be the same, because there will be some people who do have that birthday on the 29th of February in a large group of people. Yes. So let's not focus on that any longer.
Well, yeah, but it's good to have the question. We really appreciate the question.
I think so.
I'd like to say what my favorite thing is with all of this is that it's so simple. If you catch that you're looking for all of one or a minimum of at least one of the other. All we have to do is work out what it is for all of them being the same, and then 1 minus for, you don't have to do loads and loads and loads of calculations, just work out for the top line, make that top line the one that you're not using, and then 1 minus that is your answer. I love that.
Yeah, the other thing we should remember, guys, is from our results, when we say at least this is what happens, remember that is the minimum. It could be more, but we are definitely sure that at least it should be this kind of a probability.
Think of this spiral of learning and how we've gradually built on what you can do earlier, and when we get to, you've got plenty of material here that will go right through to the school leaving year, but there's simple enough material to do with years 6 and 7, and we're repeating the same sort of calculation each time, this 1 minus calculation.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.